Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. We're in multivariable calculus. This is chapter 0, which is differential equations. 0.4 specifically is second order differential equations. Last time what we did was homogeneous second order linear constant coefficient ODEs. This time what we're going to do is we're going to try to find particular solutions to non-homogeneous second order linear constant coefficient ordinary differential equations. That's a mouthful. And then we're going to discuss the method of undetermined coefficients. Basically, to solve, what we have to do now is we're going to have a y prime prime plus b y prime plus c y. Those are the constant coefficients, second order linear, and now non-homogeneous. We're going to have an f of x in there. Now, how do we solve this? When it was 0, we had a theorem that gave us 3 cases based on the roots of the characteristic equation. We can systematically solve when it's homogeneous. We have 3 cases based on those. Now that we have an f, we're going to have to build in the next couple of videos, what do we mean to find the most general solution to this one where it's non-homogeneous? It's going to turn out that the most general solution is a linear combination of the associated homogeneous solution. We solve the system as if the f was 0, and then what we have to do is find at least one particular solution to that non-homogeneous equation. And then the most general solution is the linear combination of the homogeneous solution and the particular solution. That is the general solution. Therefore, what we have to do is we already know a systematic method of computing the homogeneous case. That was the previous video. What we need to do now is in 2 videos get 2 different methods which both have pros and cons of finding a particular solution to a non-homogeneous equation. Then we will do 2-step part. We will find the homogeneous solution. We will find a particular solution using either undetermined coefficients or the variation of parameters, which will be the next video. And then once we have that, we can find the general solution to these non-homogeneous equations by writing the linear combination of homogeneous and particular. Let's get to that. Okay, before we start, let's give the definition of a particular solution, and then we're going to ask ourselves the 2 main questions about these non-homogeneous second order constant coefficient linear ordinary differential equations. Definition: given an ODE of the form ay prime prime plus by prime plus cy equals f of x, now where f is not identically 0. If it's 0, you can go to the previous video. This is the homogeneous case. We're done. If it's not 0, we need to now solve this or find all of the solutions, but finding all of them is a task. It's like, at first they were like, just let's find one, and they call that a particular solution. So literally, a function yp is called a particular solution if it solves the ODE, i.e., if we put y prime in there, you'll get, when you take its first derivative and multiply it by b, and you take its second derivative and multiply it by a, and then add that to c times that function, you're going to get exactly f of x. A solution is somebody who makes that true. The question now should be immediately, I know the definition is easy. It's like, yeah, that's an obvious definition. It's a particular solution if it's a solution to the system. It's like, yeah, that's exactly what we mean. The real question you have to ask yourself is not the definition. The definition is meaningless. How do I find particular solutions to a non-homogeneous equation? And more importantly, once I found one, is that all of them? Or have I solved this ODE? What we really want is question 2. How do we find the general solution or all the solutions to non-homogeneous second order constant coefficient ordinary differential equations? That's a mouthful. Today, what we're going to do towards answering that is we're going to give one of the 2 techniques for finding particular solutions. Once we have that, we'll put it all together and we'll show that the most general solution to these non-homogeneous is the homogeneous solution added to the non-homogeneous solution. Let's do the first method, which is called method of undetermined coefficients. Example 1, what we're going to do is reverse engineer and show you how I would get the idea of finding a particular solution and this thing that we're going to call the method of undetermined coefficients. Here's a non-homogeneous second order constant coefficient linear ordinary differential equation because 3x is not identically 0. What we're going to do first is show that I've already someone's cooked up somewhere a particular solution. So I'm going to show that it is a particular solution. What do we mean by that? I'm going to take its first derivative, its second derivative, which will be nice as 0. And then I'm going to plug it all in there. And then hopefully when we simplify, we get 3x. And that means that it worked. That's not the magic though. How do we get this? And where are we getting this so that we could put it in there and check? That's the real question we want to do. And that will be the method of undetermined coefficients. So what we're going to do instead is in part 2, we're going to derive this function by making a guess of this is a degree 1 polynomial. So we're going to make our guess a degree 1 polynomial with all the terms, and then we're going to differentiate, and that will become the method of undetermined coefficients. Baby steps, we'll just do a polynomial. In my next example, I'll just do an exponential function. And in my next example, I'll just do a sine or a cosine function. And then the worst case scenario is you'll get x to the n times e to the rx times cos mx or sine. And then that's going to be the non-homogeneous part, and that will be the general. Here's the method of undetermined coefficients. Somewhere along the line, we're going to have to talk about superposition. For now, 1. This is the easy part. I have y particular is 3 over 2x minus 9 over 4. That means y particular prime is 3 over 2, and y particular prime prime is goose egg. Therefore, what do? I put that all into my equation. That says that y prime prime plus 3y particular prime plus 2y particular equals, now I have 0 plus 3 times y particular prime, which is 3 over 2, and then what we're going to get is now plus 2 times y particular, which is 3 over 2x minus 9 over 4, which is going to give me, when I simplify, 9 over 2 plus cancel, distribute that one in there. This gives me 3x minus 9 over the 2 and the 4 cancel to give me 9 over 2. Oh, sacre bleu. Of course, that's what we wanted. That says that, check, that is a particular solution. But the real question is, how did you get the function so that you could make sure that it works? And then the second question is, eventually, is that all the solutions, or did we miss some? And yes, we've actually missed some. We would need to do a combination of the homogeneous solution and the particular solution for the most general solution. We'll get there eventually. For now, yes, it works. How did we get it? Now let's see how we derive this. All right, to start by rote learning what the method of undetermined coefficients is, we're going to see that for our non-homogeneous ODE, we had that f of x was 3x. I write it the way that we see it, and then hopefully you will see this. This is a degree 1 polynomial, so it should have all the degree 1 polynomial terms and lower. So this is 0 times x to the 0, or 0 times 1, which usually we don't write. Our function is this. But you want to see that because what we do all the time is, if you have a polynomial, what you're going to guess is a polynomial of the same degree. There will be a couple caveats when we start adding e and sine in there. We have to depend on the roots of the characteristic equation, but we won't do that right now. I just mentioned it. So if we have a degree n polynomial only as our function, we're going to make a guess of the same degree polynomial. We have undetermined coefficients a and b, and we would like to determine what they are. I'm going to do the exact same thing we did with this guy, except now it's a and b. And so I'm going to take the first derivative, the second derivative, put them into the equation, solve for the appropriate coefficients, and see what the a and b are. And then this is why we call it the method of undetermined coefficients. These are undetermined, and we're going to find them by plugging them into the equation. Doing that, I'm going to plug this into, I'm going to take the first and second derivative and put it in there again. Y particular prime is a. And then y particular prime prime is 0, just like the first time because it was a linear function again. But this time now we get 3, 0, this one, and then 3 times a plus 2 times ax plus b is equal to 3x plus 0. One or two polynomials is equal if and only if all of their coefficients are equal. We're saying this degree 1 polynomial is equal to this degree 1 polynomial. So I'm going to simplify everything and match the coefficients, and this is where we get a linear 2x2 system to solve for a and b. What? Simplify this. This gives me 3a plus 2ax plus 2b equals 3x plus 0. If I group all of these together, this is going to give me 2ax plus 3a plus 2b equals 3x. Now, if this polynomial equals this polynomial, this coefficient has to match this coefficient, and this coefficient has to equal 0. What that tells me is immediately 2a has to equal 3, or a has to equal 3 over 2. The coefficient that we were looking for, and then that immediately says from here 3a plus 2b is equal to 0, and that says 2b will be equal to negative 3 over a, which is negative 9 over 2, and then we're going to divide, and that's going to be negative, that should be a 3, I was jumping the gun. That'll be negative 9 over 4. Now I've determined what those coefficients were, and that's how I am going to build that function. We're going to look at what the non-homogeneous function is, and then we're going to train ourselves to make a guess based on that with undetermined coefficients. And then we're going to take the derivatives, put them in there, find the coefficients using a linear n by n system depending on how many coefficients we have. Then we have a method of finding the particular solution to non-homogeneous second order differential equation. What we're going to do with that then is use the particular solution and the homogeneous solution to find the general solution to these ODEs. Also notice that I found this particular solution with this method, which we're going to call undetermined coefficients, and all I did was take derivatives. I cooked up a fairly easy one to show you the method, but there's going to be a second method. You're like, well, why would you ever find another method? Because it turns out you can't use this for every kind of function. You can only make this clever guess, and it only works out if you use particular kinds of functions. If I put a tan x there, this is the classic one that they always do, that's sine over cos. I have no guess to make, and so I can't use undetermined coefficients for certain non-homogeneous functions. But for polynomials and exponential functions and sine and cosines, we can make this nice guess. The advantage to that is all we're ever doing is taking derivatives and then solving linear systems. The downfall to that procedure is you get bogged down with computing horrible derivatives possibly, and you now have to know linear algebra to solve n equations and n unknowns. This was 2 by 2, so I just did it ad hoc, but if you have 15 unknowns, you're going to have to set up a big 15 by 15 linear system and find all of those undetermined coefficients, which is not going to be super fun. But nowhere in this process that I need to integrate, only differentiate and solve linear systems. The other method is going to be variation of parameters, and in that one we're going to have to integrate, so there will be none of this solving linear systems or horrible finding undetermined coefficients, but you're going to need to know how to integrate well, up to including sometimes you get the integral of e to the x squared dx, and then now you have to leave that as the implicit solution because this is a non-elementary function and I can't find the antiderivative using elementary techniques. So there's pros and cons to the two methods. This is the first method called undetermined coefficients. Let's do another one. Okay, for the next one, we're going to try and find, we're going to find a particular solution to, notice that I'm going to use the same left-hand side, and we're going to change the non-homogeneous function. This will be what eventually we talk about superposition. If we had to add plus the 3x from the previous video and we use the same one, we can solve this one and then we can solve the other one separately and add those. Superposition just means you add those solutions. We'll get to that in the next video. For now, there's going to be three main forms of guesses that you're allowed to use for undetermined coefficients. If it's a polynomial, you can make a guess. If it's an exponential function, you can make a guess. And if it's a sine or cosine function, you can make a particular guess. And then you can have the worst case scenarios where you multiply a polynomial times an exponential times a sine or a cosine, and then we have guesses for those. And that will be the method of undetermined coefficients. The downfall is it only works for those specific categories of functions. So as soon as you have a non-homogeneous where it's not one of those categories, we can't use the method. The good part is anytime I do have those, and these ones are the ones that come up a lot of time in nature anyways, exponential, sinusoidal, and polynomials are going to be what comes up anyways, so luckily that's what's going to happen. But once in a while, if you get a tan or something, I can't use the method. But you'll see again, all I'm going to use is differentiation to find out what the particular solution is. To do that, I need, again, my non-homogeneous function is 10 e to the 3x. Therefore, what I'm going to do is I'm going to guess this time that my particular solution is some undetermined coefficient a times e to the 3x, because when I take the derivative of this now, I'm just going to get a 3, but it will preserve the form of the exponential function. Therefore, when I take the first derivative, y particular prime is equal to 3a e to the 3x, and y particular of x prime prime is equal to 9a e to the 3x. Now what I'm going to do is plug that into the equation. That tells me that now 9a e to the 3x plus 3 times 3a e to the 3x plus 2 times y was just a e to the 3x equals 10 e to the 3x. And now e to the 3x is never 0, so we can get rid of it on both sides. But first of all, let's clean everything up if you don't see that. That tells me that I have e to the 3x, e to the 3x, e to the 3x, e to the 3x in all the terms. So we could cancel it, but right now just group everything together. I have 9a, and then 3 times 3 is 9a again, and then 2a. So I have 20a e to the 3x equals 10 e to the 3x. And then now, because e to the 3x is never 0, I can divide by or multiply both sides by e to the negative 3x to cancel that. And then I'm going to get 20a equals 10, or a equals 1/2. Therefore, we found our particular solution. Y particular of x is 1/2 e to the 3x. Do you believe me? Let's check. We're going to do this problem in reverse order of the previous question. Now that I found it using the method of undetermined coefficients, let's just check on an exam whether I did it right. What that tells me is what's going to happen. I have to erase all of this and then redo it again. It looks like I'm doing it again. Plugging that in, what we're going to get is y prime prime is 9 over 2 e to the 3x plus 3 times 3 over 2 e to the 3x plus 2 times 1/2 e to the 3x. I plug everything in. Simplifying, I'm going to get equals 9 over 2 e to the 3x plus 9 over 2 e to the 3x plus e to the 3x. Or you can leave it in this one, it makes it convenient as 2 over 2, then I have the same common denominator. Anyways, that's going to give me 9 plus 9 plus 2 is 20 over 2 e to the 3x, which is 10 e to the 3x, which is the function that I got. So this is a particular solution to this. Let's do one more where we have a sinusoidal function in there. For our last example, what we're going to do is use a sine or a cosine function. We're using the same left-hand side again, and then what we'll do is we'll tie that in with superposition, and we'll write those three terms, 3x plus 10 e to the 3x plus sine x, and you use superposition, whatever the heck that is, to find the general solution to that linear combination of functions. Not linear combinations, that combination of functions. Now what we're going to do is find a particular solution when we have f of x is sine x. Our non-homogeneous function is sine x. We may just want to guess. What would our guess be? We're going to guess now. If it's in this form, we're going to guess our particular solution is going to be a sine x. We may think that that's what we're going to get, but if I think about this for a second, as soon as I take the derivative, I'm going to introduce coses, and there's no coses in here. So how we get around that is we just do this. Classically, actually, what we're going to do is we're going to write this as a cos x plus b sine x. It doesn't matter. Once you fix the a and the b, we solve for a and b. This is the guess. You don't just guess which one it is because sine and cosine turn into each other up to a negative in their derivatives. We're going to guess that this will be the most general guess if we have a sinusoidal function, sine or cos, as our non-homogeneous function. Once I make that guess, the technique is now the same. Every time you make a guess, you have to practice knowing, based on the function you have, if you're going to make a guess, you have to practice getting that guess. We're going to make a big overview of that in a second. But this is the guess I have. Now the procedure is the same. You take the first derivative, you take the second derivative, plug that into the ODE, and solve for the undetermined coefficients. Therefore, I need y particular prime is going to be negative a sine x plus b cos x, and then y particular prime, yeah, this one's going to be less fun. You're going to start seeing why undetermined coefficients is not so fun, because we're going to have to plug all of those things in, simplify, and then find the coefficients. Y prime prime is going to, and they're not ever going to go away. Polynomials disappear and stuff. That's not going to happen this time. This one is going to become now, the derivative of this is going to be negative a cos x minus b sine x. Once I have those, what do I do with them? I plug them in. That tells me that y prime prime negative a cos x minus b sine x plus 3 times y prime is negative a sine x plus b cos x plus 2 times my function a cos x plus b sine x equals sine x. Now we're going to do the same thing. We're going to match, and that's 1 sine x plus 0 cos x, remember. This is now, I'm going to simplify. I'm going to group all of the coses together and all of the sines together. Once I do that, what do we get? Put those together, we are going to get these coefficients in front of cosine and these coefficients in front of sine, and now what we're matching is 1 technically times sine and 0 times cos, and that's never there. And you're like, what do I do now? We're matching coefficients. If these two statements are equal, whatever's in front of cos has to equal whatever's in front of cos on this side, and whatever's in front of sine on this side has to equal whatever's in front of sine on this side. That's going to give me a linear 2x2 system again. What does that give me for in front of the sine equation and the cos equation? For sine, this is going to give me, I have negative 3a plus b equals 1. And for the cosine ones, I'm going to get a plus 3b is equal to 0. What that immediately tells me is from this one that I have that a is equal to negative 3b. I can plug that into here. That's going to give me from this equation, that gives me negative 3 times a, which is this, negative 3b, plus b equals 1. And that's 9 plus 1. That gives me 10b equals 1, or b equals 1 over 10. And then from that, what is a? A is negative 3 times b, which is 1/10. So a is negative 3 over 10. Either way, I now have those determined coefficients, and now I can put that into my particular solution. What does that give me? That gives me my particular solution, y particular of x. I now found them. A was negative 3 over 10 cos x, plus b was 1 over 10 sine x. You check that that actually works in here. Put that back in. You better get when you simplify sine x. Now let's recap those 3 types of guesses and put it all together into a theorem for how you make guesses for undetermined coefficients. All right, we're going to break this into 2. The method of undetermined coefficients A and B, mostly because I couldn't write the second half on the board. You're going to be given a constant coefficient second order linear ordinary differential equation, and if you have it non-homogeneous and you get some k times a polynomial times an exponential, if that's the form that you get, including if r is 0, then you could have that, and if the m is 0, you could have the 2 cases we just did. If you have something like that in combination, then what we're going to do is we're going to make the guess y particular is x to the s. Just a second where that comes from. We'll have to do another couple examples in the next video explaining this in more detail. For now, you have to contemplate or go look up one and see when this goes wrong. Our particular guess is going to be x to the s times what our normal guess would be. We guess if it's a degree m polynomial, we make a general guess of a general degree m polynomial. If we have e to the rx, we multiply that by e to the rx. And why are we doing this? So you're going to either multiply by x to the 0, which is just a 1, or you're going to multiply by x to the 1, which is an x, or you're going to multiply by x squared, which is x times x. But when do we do this? The cases we had, if it's not a root of your auxiliary equation, you don't have to multiply by anything. If it is a single root, you multiply by x to the 1, and if it's a double real root, you multiply by x to the 2. We'll do that in the next video to show you specifically how that's going to work, and if it doesn't work out, how can you tell if you didn't make the guess right? If you're supposed to make this guess where you're supposed to multiply by x to the 1, and you make the guess where you multiply by this, you'll just get 0 equals 0, or you'll get a contradiction when you try and solve for all the a's and b's. Something will go wrong drastically, and that is usually the hint that you forgot to multiply by one of these and you didn't check your auxiliary equation. I'll wrap this up a little bit better when we do the general solution to these non-homogeneous equations, because we have to do the linear combination of the homogeneous and the particular, and then you'll have in your mind that you should have this auxiliary equation involved. Right now, it just seems like all of a sudden we're like, by the way, make sure that you check your auxiliary equation and multiply by the appropriate power of x. Long story short, yes, at first, this is, if you get this, this is the type of guess you make. Now let's do part B, where if you get a sine or a cosine, we're going to make similar guesses, but we have to talk about the complex conjugates. Let's do that. For method of undetermined coefficients, part B, if we have now second order constant coefficient linear ordinary differential equation, which is non-homogeneous, if we have the form k times a polynomial times e to the something times cos beta, or e to the something times sine beta x, if we have either of those, we're going to make this horrible guess as a linear combination of the polynomial times the exponential function times the cos function, and then plus another polynomial of degree m times that same exponential function times the sine function. And then we're still going to have the x to the s. It will be 0, and you won't have to multiply if that complex number is not a root of the auxiliary equation. We multiply by x to the 0, or we leave it alone if that complex number is not a root of the auxiliary equation. And we will multiply by x to the 1, or x, if that complex number, and therefore its complex conjugate, if a complex number is a root to a polynomial, so is its conjugate. They come in pairs. Anyways, if those are roots of the auxiliary equation, we multiply by x to the 1. In the next video, what we'll do is we'll do a couple examples where we show where we have to multiply by the 1 or not multiply by the 1, depending on what the auxiliary equation is and what our exponential values are, and then go on to do another method which what happens when I don't have one of these forms of this or the ones in part A. Hands the air and we just quit? Well, at first, yes, but then we regroup, we get more machinery, and we get a different technique called variation of parameters, and that's what we're going to do next. Please subscribe right here, hit the notification bell. I'll see you next time.